Hey everyone, and welcome to this explainer. Now you likely already know the basics of driving, but today we're going to completely deconstruct the hidden mechanical symphony that you actually command every single day. We're diving deep into the absolute engineering marvel under the hood, breaking down the highly complex systems that make a drive possible into logical and honestly, really fascinating steps.
Okay, let's dive into this, because simply turning the key kicks off a perfectly synchronized chain reaction. Today we're tracing that exact chronological path, from the very first electrical spark all the way to the rotational force turning your wheels, and finally, the hydraulics that bring all that forward momentum to a safe halt.
All right, Section 1, the electrical starting system. So, before a single drop of fuel even begins to burn, we literally have to wake the machine up, right? And this happens through a beautifully seamless three-step handoff. When your engine is off, your car's battery is the only source of power. You turn the ignition and boom, the battery sends this massive initial burst of power. We're talking hundreds of amps, which is literally enough electricity to weld metal, straight down to a small electric motor called the starter. Now, it takes this tremendous amount of energy just to spin a cold engine, because that starter has to overcome all the internal friction and the intense compression pressure inside the cylinders. It forces the engine to spin just a few revolutions, getting everything moving so combustion can actually begin. And once the engine catches and starts running on its own, its spinning belts power the alternator, which immediately takes over the job of generating electricity.
It's incredibly important to clarify the distinct roles here, because they get misunderstood all the time. The battery is really just there for when the engine is off and to provide that one initial massive burst to the starter. Once the engine is on, the alternator becomes the true powerhouse. Inside the alternator, you have the spinning rotor of magnets passing over conductive copper wiring, which generates the electricity for your headlights, your radio, the computers, all while simultaneously recharging the battery. So the key takeaway is this. If you have a brand new battery, but your car is still having electrical problems while it's running, the issue is almost never the battery. It's usually a failing alternator.
Moving right along to Section 2, the four-stroke engine cycle.
Now that our electrical system has successfully woken the car up, we transition to the actual beating heart of the vehicle, the internal combustion engine. This is where high-energy density fuel is miraculously converted into physical, mechanical motion. Whether your car has 4, 6, or 8 of these, the basic fundamental unit of this architecture is the cylinder, a heavy metal chamber. Inside that chamber sits the piston pumping up and down. Down below, a connecting rod attaches that piston to the crankshaft, which magically translates that up and down motion into rotational motion. Up at the top, you've got valves to let air and exhaust in and out, and a spark plug sitting right smack in the center, just waiting to ignite the whole shebang. Almost every single passenger car out there with a gasoline engine uses a very specific four-stroke combustion cycle to create this motion, known as the Otto cycle. These 4 strokes happen in a strict sequence: intake, compression, power, and exhaust. During intake, the piston moves down, sucking in a highly combustible mixture of air and gasoline. Next is compression. The valve snaps shut and the piston moves back up, squeezing that mixture incredibly tight. Then comes the magic, the power stroke. The spark plug fires, the highly compressed gas explodes, and that massive expansion of gas forces the piston violently downward. Finally, in the exhaust stroke, the exhaust valve opens and the piston pushes the burned, leftover gases straight out the tailpipe. And remember, this entire 4-step cycle, it's repeating thousands of times every single minute. In fact, when you're cruising at highway speeds, this explosive cycle is happening over 25 times a second in every single cylinder. It is wild.
It's really an elegant mechanical translation. Think of the intake stroke exactly like pulling back the plunger on a syringe to draw in fluid. And as that massive explosion forces the piston down during the power stroke, the continuous heavy rotation of the crankshaft pushes the piston right back up, effectively resetting the cannon for the next explosion. It's a continuous, breathing life cycle, very much like a human heart, really, where fuel is the food, air is oxygen, the spark is the heartbeat, and the exhaust is just waste removal.
Let's move to Section 3 and see how this builds: transmission and the differential.
So, having a spinning crankshaft is great, but it doesn't do us any good whatsoever unless that rotational energy actually reaches the pavement. If we pull back to the macro view, we see this beautifully unbroken chain of motion. A drop of fuel burns, forcing the piston to move. That up and down movement forces the crankshaft to spin. The crankshaft then connects to the transmission, which uses a clever series of gear ratios to manage that power. And then that rotational force is sent straight down a drive shaft to finally rotate the wheels. It is a direct physical lineage of energy from a tiny explosion all the way to the spinning tires propelling you forward.
But getting power to those wheels introduces a really fascinating physics problem. Think about this for a second. When your car goes around a corner, the wheels on the far outside of the turn actually have to travel a longer distance than the wheels on the inside. Because speed equals distance divided by time, those outside wheels absolutely must travel at a higher speed. If your car's driven wheels were just locked together on a single solid piece of metal axle, they would be forced to spin at the exact same speed. Trying to make a turn would be incredibly difficult, it would put heavy, damaging strain on your axle, and one of your tires would literally have to slip or skid across the pavement just to make the corner.
The mechanical solution to this physics problem is brilliant. It's called the differential. Power comes in from the engine via the propeller shaft, which turns a smaller pinion gear. That gear meshes perfectly with a much larger ring gear, often called a crown wheel. Tucked inside this assembly is a cluster of smaller spider gears. What this completely ingenious mechanism does is take the single input of rotational energy from the transmission and precisely split it across the two wheels. It constantly aims engine power at the driven wheels while simultaneously allowing them to rotate at completely different speeds. This completely eliminates the skidding issue and gives you perfectly smooth cornering.
And finally, Section 4, Hydraulics and Braking Systems.
So, we've created thousands of controlled explosions, we've elegantly delivered that power to the turning wheels, but now we've got a heavy 2-ton vehicle hurtling down the road. How do we stop? Most modern cars safely arrest all this forward momentum using a dual-circuit hydraulic braking system. It honestly works like hydraulic magic. When you push your foot down on the brake pedal, you're actually depressing a piston inside a master cylinder. This forces specialized brake fluid along a series of tightly sealed pipes all the way to smaller slave cylinders located at each individual wheel. Because liquids literally cannot be compressed, that fluid pressure distributes itself instantly and evenly, forcing pistons at the wheels outward to apply the brakes. But doing this with just your foot power alone would be absolutely exhausting. So cars use a power-assisted servo unit. This servo leverages the vacuum created by the engine's air intake to massively multiply the physical force you apply to the pedal.
At the wheels themselves, this intense hydraulic pressure creates friction in one of two ways. Disc brakes feature a metal disc that turns with the wheel. Hydraulic pistons force heavy-duty friction pads to clamp tightly against this disc from both sides to slow it down, kind of like squeezing the brakes on a bicycle wheel. Drum brakes, on the other hand, feature a hollow, rotating drum. Here, hydraulic cylinders force curved, lined shoes to expand outwards and press hard against the inside walls of the drum. You'll very often find disc brakes on the front wheels and drum brakes on the rear. Why is that? Well, because when you brake, inertia throws the immense weight of the car violently forward, meaning your front brakes have to do the vast majority of the heavy lifting to bring you to a stop.
I also really want to highlight an amazing modern advancement we're seeing in hybrid and electric vehicles: regenerative braking. In these systems, when you take your foot off the accelerator, the electric motor actually reverses its role and acts as a generator. So instead of just creating pure waste heat through friction like traditional brakes, it uses the forward momentum of the car to produce electricity, feeding it right back into the rechargeable battery. It adds this extra resistance to efficiently slow the car down in city driving, all while actively recovering energy. It's a real game changer. Which brings our incredible journey perfectly full circle. A car engine isn't just a mysterious black box of magic. It is a beautifully timed, continuous cycle of fuel, air, spark, and motion. From the starter waking the entire system up, to the differential smoothly guiding you around those tight corners, to the fluid dynamics bringing you to a safe, controlled halt. It is a true mechanical symphony. So I have to ask, the next time you get behind the wheel, are you going to just drive? Or will you actually feel those thousands of perfectly timed explosions and synchronized systems working right beneath your feet? I really hope this explainer has left you looking at your daily commute in a whole new, awe-inspiring light. Thanks for joining me on this journey, and I'll catch you in the next one.